So I start with lecture 7, and this is the last part of the topic of X-ray diffractometer. Here we are going to just check on what are the different parameters that needs to be controlled, or different inputs that needs to be put in when we are actually using an X-ray diffractometer machine. And to begin with, we have to understand the parameters, and before we understand the parameter, just list them down. Okay, the first parameter that is there is called the scan range. Okay, so you have a scanning range from, because as I have shown you the other day, the machine which is there, you basically have the goniometer, and then here if it is your sample, your X-ray tube is on this side and the detector is on this side. So depending on your configuration, either your detector is fixed or your sample is fixed. But if you consider the theta to theta configuration, this will become more or less fixed. So the sample will rotate and the detector will also rotate at an angle 2 theta, right? So that is the range angle that we have. So by scan range, I mean that what is the angle that we have here. Okay, so the first point is that the start and end angles to scan. So usually it is from 10 degree to 80 degree. Okay, so the range is not that large. The reason is, there are reasons. Okay, let's go to the next point first. Can be used to make optimal use of a given measurement time. So what happens is, sometimes your sample, suppose, and you are expecting a peak between, let's say, 30 and 70 degree. So you don't really do a scanning from 10, you start from 30 and end at 70. That also saves a lot of time. Okay, and depending on how precise you want to be, you can also adjust the scan speed, which will again save your time. Okay, so this angle plays that role. Now very low angle is usually not used. It is used only in case of exceptional cases. Okay, in case you are sure that below 10 degree there is some kind of plane or Miller indices that is possible to obtain, or that might be there, or your sample is something which is new in nature and you want to know about the complete properties, then only you are using that case. Usually it's always above 10 degree. Now basically what happens is, if this angle becomes very low, okay, if this angle becomes very low, and if the sample keeps on rotating, and let's say this angle is very low, let's say around 2 degree. Okay, now if this angle is 2 degree, what will happen is, the ray from the X-ray will go directly into the detector without any diffraction, and this, what happens is, will destroy the detector. Okay, because there is a direct exposure to the primary beam, which I don't want. So we don't go below the angle which is actually not suggested. So it is always better to keep it below 10 degree. Okay. Okay. So next we have got something which we call as the scan speed. Now you want to scan and you want to know the angle, then what speed you should scan the first angle, let's say. Okay, that means that, let's say, 1 degree you are scanning at a speed of 1 second. So 60 degrees you take 60 seconds for the entire scan to get over. Okay. So the scan speed also determines the time. So if the scan speed is slower, okay, if the scan speed is slower, the scan will definitely be better, and the signal to noise ratio will be actually averaged out. Okay, so I'll tell you what is signal to noise ratio in the next slide. So now, right now, what is important is that this signal to noise ratio should be high, so that you are actually getting a good representation of the entire crystal structure. Okay, so we use a slower scan rate, but in case you need a fast scan rate for doing an approximate estimation of the sample, that can also be done. But you have to remember that the scan speed does not influence the resolution. I hope you remember the term resolution, to resolve two very close points, or to observe two very close points, or to differentiate two very close points. So in order of a crystal structure, if the two atoms or molecules are very close to each other, and we can actually determine them using XRD, that means the system has got a very good resolution. So we also have the limiting factor of the number of samples to be measured and the time available. So there are a lot of restrictions when you are actually practically using the machine in real life. Okay, so what happens here is, so that was our scan speed. Next we will go for source power. Okay, so what you have is the intensity of the X-rays, with how intense the X-rays you are basically going to use. That will depend on what is the voltage and the current you apply to the input. So the source power is basically controlled by two parameters. The first is the voltage of the X-ray tube, which would be 40 kilovolt, which is actually suggested. Okay, usually it is 40 kilovolt, and the current will be actually nothing but 30 milliamperes. Okay, that is the suggested value. Some variation might be there in case some specialized experiments are done. Okay. And one more point to note here is that the value of the voltage should always be higher or equal to the current. Okay, because what we need is we are going to get a power here. So if you want power, it's basically nothing but current into voltage. Okay, and we need to strike an optimal position here, optimal power. Okay, and for that usually voltage and current can at max be equal. Okay, or voltage should always be higher or equal to the current. Okay, this is why the instrument has some kind of restrictions there. Okay. Next we have got something which is called the stepped width. So basically you want to scan at what angle? So you are basically, let's say, rotating the sample. Okay, you want to rotate it at every step. You want to rotate it at 0.1 degree or 0.2 degree and so on. That is what is called the step width. Okay, so if you look into the points of a step width, what happens here is that the diffractometer is equipped with a point detector. So the measurement will definitely proceed along the 2 theta circle step by step. So this is your 2 theta circle, and the measurement will proceed step by step. So it will rotate at some angle the sample, and then it will be going for the next angle and so on. Okay. So the increasing the step width with a fixed scan time means that there are fewer points in the diffractogram which are measured for a longer time. So what happens is, if you are actually increasing the step width, so that means if you are going from, let's say, let's say 1 degree to 2 degree, 1 degree to 2 degree, so you have increased the step width. Okay, with a fixed scan time. So scan time you have fixed it. Okay, that means there are few points in the diffractometer which are measured for a longer time. So that means 1 degree to 2 degree, in between there is nothing measured. But if you let's say from 1 you go for 1.5 degree, that means you have got a 0.5 degree. So the step width has been increased. So there are more points which can be measured by the diffractogram. Okay. Now this increases the signal to ratio, noise ratio. This will actually increase the signal to noise ratio which we need, but the point here is it will definitely reduce the resolution. Why? Because by resolution we mean we will need to scan to very close points. Now if you are not putting that particular plane at that particular angle, you are definitely not scanning that at that particular point. So the signal to noise ratio definitely increases. You get a good signal, but then it will also reduce the resolution which you don't want. Okay. So what is the correct choice? It will basically depend on the nature of the experiment. So what is your observation, what are your requirement, based on that you are going to get that. Okay. So next we have got something which we call as the slit width. So I think slit we have discussed it in the last lecture. There are different kinds of slit, the divergence slit, okay, and so on. Okay. So if you consider the slit width and slit width here. So the slit width, depending on the type of slit width, there are 3 slits that control the divergence of the X-ray beam, and this will actually control both the intensity and the resolution. Okay. So there is something which is axial and something which will control the height. Okay, axial and height divergence. Okay. So I think when we discussed, we talked about the axial divergence, the anti-scatterer slit and the receiving slit. So the receiving slit and the anti-scatterer slit are basically on the detector side, and the axial divergence slit is both on the detector side and on the X-ray tube side. Now this divergence slit is actually given in degrees, and the anti-scatterer slit is also given in degrees. The receiving slit width is given in nanometer. Okay, so this is how you actually adjust this. So closing the slit actually and obtaining an optimal position is also very important, because this will actually improve the resolution, because we will have a very fine ray of X-ray falling on a particular point. We won't have a broad spectrum of X-ray falling, and as a result the expense resolution will increase. But then there is a problem, the signal to noise ratio will again decrease. Okay, so the point here is that the resolution and signal to noise ratio doesn't go hand in hand. If one increases, the other decreases, and vice versa. So we actually have to strike an optimal condition to get the get a very good result. Okay, so the settings that we usually use for a good signal to noise ratio is 1 degree is to 1 degree into 0.3 millimeter. So I hope you understand this. Okay, because 1 degree is for the axial divergence, 1 degree is for the anti-scatterer slit, and receiving slit will have a width of around 0.3 millimeter. On the other hand, when we talk about the high resolution, this is the appropriate measurement. Okay? This is the appropriate settings that we should use or we can use. Okay, the next we have got times per step. Okay, so next we have got time per step. Okay, sorry, so we will go for time per step here. So how long is spent scanning at each angular step? So if you have got the angular step, how long does it take for at each step, how much time should it spend? That is important. Okay, so if you want to get a very good peak with a good intense peak, you need to spend more time on a particular angle. So increasing this parameter, what happens, will lessen the noise, because the average reading will be more representative of the real structure. So if you are scanning a particular point for more time, the noise will definitely reduce, because you are going to get more and more signal from the crystal structure, and it will actually represent the crystal structure and not any stray signals. Okay, it will also result in higher peaks on the output graph due to an overall increase in the amount of X-rays produced at each step. So this is self-explanatory. I hope you understand this point, right? Because if you increase the time, you are going to get more signal, the intensity is going to be more, and because you are going to get more and more X-rays from that particular crystal plane. Before we proceed further, we need to understand what is signal to noise ratio and resolution. But I think you already know what is a noise. If you are using any electronic device, there is a lot of noise which is involved. Noise in general, we can say, are the unwanted signals, which I am not really interested in. If you are actually having an X-ray coming out of the X-ray tube, it will basically have a K alpha, K beta and lines and all. But if you are using only the K alpha line, that means K beta can be considered as a noise. So what do? You use a filter, okay, both at the receiving end and as well as at the end where the X-ray tube is placed. Okay, so this is basically a kind of noise. So this is just an example of noise. If you use an electric circuit, you also have a lot of noise. So basically what happens, signal to noise ratio. So if you have a signal on this side and the noise ratio is here. Okay, now if you have a high value, okay, if you have a high value here, what does it mean? That the denominator should be higher value and the numerator should be lower value. Okay, so that means the noise is less and the signal is high. So that means the signal to noise ratio is high. That means you are getting a very good signal. Okay, so the ratio of the strength of an electrical or other signal carrying information to that of the unwanted interference. Very simple definition. Now on the other hand, if the signal is low and the noise is high, okay, you are going to get a very low value on this side. So low value means signal to noise ratio is having a low value. Okay, it can be measured in terms of decibels. So if this is a low value, what does it mean? That it is basically having more noise compared to signal. Okay, so I want more signal compared to noise. So I think it's very simple here. What is resolution? Now resolution, as I told you in the previous slide, resolution is the smallest distance between the crystal lattice plane that is resolved in the diffraction plane. So if you have two crystal lattice points which are very close to each other, and we can actually observe that in the XRD, that means the system has got a very good resolution. Now if that distance which it can resolve, the XRD machine, is 4 angstrom, angstrom is 10 to the power minus 10 meter, that means the resolution is very poor and low. On the other hand, if it can resolve the crystal planes with lattice which are very close, let's say for example 1.5 angstrom, we can say it is a very good resolution instrument. Okay, so based on this, actually we also determine the instrument. But before we can really proceed with the experiment, we need to prepare the sample. Okay, now this sample can be powder sample, can be thick film, can be thin film, can be single crystal, and so on. But in most of the times when you are doing your experiment, let's say in your next semester when you are doing your project, there also you are going to work on materials, and in the lab we are basically working mostly on nanomaterials. So if you are working on nanomaterials, you are mostly going to prepare powder sample. We do have a powder XRD in the system, in the department, so we are going to use a powder XRD there. Okay, so this slide is also very important, and each of these points you should remember. Okay, and please keep this note intact with you, because you are going to use it in your next semester, because this is going to be important. So what is the sample preparation? Now the right sample treatment basically involves removing the undesirable substances. Now in case your sample is kind of, let's say, having moisture, you don't want that when you do your XRD, so that's an undesirable substance. You basically heat it in an oven, and then after that you can take your readings in the XRD machine. So that is an undesirable substance. So if you want to actually obtain a desirable sample, there are some of the things that we should actually consider. Okay, and what is desirable is basically nothing but the particle size, okay, the orientation and the thickness. If you are using a thin film, okay, you basically are concerned about the thickness as well. Okay, if it is too thick, it will become a thick film and not a thin film. The particle size should be considered and the orientation should be considered. Now, when we consider any powdered sample, it is grained very finely. You can use a mortar and you actually crush it manually. You cannot keep on crushing it too much. Okay, that might actually bring some changes into the sample. Also, you cannot use any kind of machines there, okay, because you don't want to use too much pressure. You don't want to actually alter the crystal structure or the phase of the sample. Okay, so if you extremely fine grain it, you're basically going to get a very good signal to noise ratio. The intensity fluctuation will definitely not vary. Okay, there will be lesser. It will avoid spottiness. What happens is in the sample you might have some kind of defects and all. Okay, so these things will also be minimized. So minimize, it will minimize the preferred orientation. So preferred orientation means certain number of planes which are actually already present there, which is too much in number, which I don't want, that should not be there. Okay, it will ensure enough particle participation in the diffraction process. So if it is crushed finely, we can have more number of particles when we are actually taking the readings. But if we do excessive grinding, okay, using some kind of machine or even manually, there will be lattice distortion and there will be a possible formation of an amorphous layer outside the grain. Okay, so we don't want that. Okay, so that is not needed. So we don't do excessive grinding of the sample. Now, if you look into the diffractogram, basically what happens is we are having a graph which is the output. It is between intensity and the scanning angle 2 theta, which I have already mentioned a number of times. Okay. Now, the quality of the powder diffractometer as mentioned will actually depend on the signal to scan noise ratio and of course the resolution. Both of them are strongly linked and only can be improved at the expense of the other. So, both of them are actually vice versa. So, if the signal to noise ratio increases, the resolution decreases. On the other hand, if this decreases, the resolution will basically increase. Okay. So, basically we need to find a reasonable compromise so that we are actually going to get some kind of good result. Okay. So, optimal condition is the important term. Yeah. Now, both machine setting and sample preparations are important for obtaining a good quality diffractogram. So, if you want to going to get a diffractogram, good quality diffractogram, you have to have both machine settings, so the parameters that I have already mentioned, and then also your sample preparation should be good. So, if we look into the diffraction pattern, the final output, visually what you can see initially is the spacing and the position of the peaks. Okay, the spacing and the position of the peak will tell you which crystal group the sample belongs to. You can actually determine which space group it belongs to. Space group is something which we have discussed in our previous lecture in XRD basics. Please refer to that, probably it's lecture 2. Now, the position of the peak describes the size of the crystal unit cell. So, you can also determine what is the size of the crystal unit cell. It means that you can determine the lattice parameter, that means A, B and C. Okay. If there is slight shift in the crystal peaks, basically the A, B and C might vary. So, in case you are expecting a sample whose A, B and C you know, which is a standard sample, and you are getting the value of the lattice parameter to be something different or too much varying, that means there is some kind of problem with your sample. Maybe you need to redo the experiment or resynthesize the sample and so on. Okay. So, the intensity values and shapes of the peak. So, the intensity value and shape of the peak, the intensity will basically give you the information of the elements present in the crystal, and of course, the shape of the peak, the symmetry and the asymmetry will actually give you the crystallite structure. Okay. This is the initial observation. You can actually do a lot of things with the XRD data, but these are the initial things that you can look into. Okay. Now, this intensity distribution is as a function of diffraction angle. Okay. So, what we do is we use this data, whatever result you have obtained, okay, and we will actually compare it, okay, with a large set of standard data. So, we use some kind of standard data which we can actually compare it, okay, and actually see whether our results are correct or not, if your sample is standard, that is. And this database, which is the JCPDS, which is now known as ICDD, okay, has got a file which is the PDF file, okay, which basically gives you the information. Okay. So, if I can just go through this, the JCPDS basically stands for Joint Committee on Powder Diffraction Standards, okay, and this was the old name. Nowadays, it is more popularly known as ICDD, which is the International Center for Diffraction Data, okay, and they will actually provide you of some file which are called powder diffraction file. These are not freely available. Basically, it comes with your XRD machine, or you have to buy it separately, because this is a very well maintained and widely accepted diffraction data, which can be used for references and even for publications. Okay, that is important. Now, what are the applications of XRD? Okay, so XRD basically applies to the pharmaceutical industry. Okay, in pharmaceutical industry, what happens is you can characterize the composition of the pharmaceutical, and XRD pattern is directly result of the crystal structure. You basically have any pharmaceutical medicine and all, you basically can do the XRD analysis, and the crystal structure can tell you whether the sample is the same what you prepared or not. Okay, XRD is basically the key technique for solid state drug analysis. Okay, and is benefiting in all stages of drug development, testing and production. So basically, initially if the drug development is made, some XRD characterization is definitely carried out, and before being released into the market, the XRD characterization is also done. It is also important in case of forensic sciences because trace elements can be analyzed using XRD. Now, example of contact traces are, let's say you have a crime scene where there is some kind of trace element and you want to detect it. You basically use an XRD machine to detect if there are paint flakes present, if there is any hint of hair, okay, glass fragments, stains of any description, or loose powdered material. So you might take an XRD of any material there, and then you might have some kind of powdered material there in the crime scene, and then you can do the XRD analysis to know what kind of material is that. So basically what we do is we can identify and compare the trace quantities of material that will definitely help in the conviction or exoneration of a person which might be involved in the crime. Okay. Next we have got something which is the geological application. Okay, I think mines and all is something which is already known to you. Okay, so if you look into the geological application, it's mostly used in mining. Okay, it's a mineral exploration. So you basically have a place where it is excavated and you are getting some kind of mineral out from there. You want to know what kind of material is there. Okay, then you can basically do the X-ray characterization, because you know each type of mineral or each type of material is characterized by unique X-ray diffraction pattern. So you can get that pattern, compare it with the PDF or the JCPDS data, and that comparison will tell you what kind of mineral the mine contains. The XRD data can be analyzed to determine the proportion of the different minerals present. So if you don't have a single mineral but a combination of minerals, you can actually determine what quantity of how much material is present in that particular location or region. Okay. Next we have got the microelectronics industry. There we use a lot of semiconductors. Okay, so we basically have the silicon and the gallium arsenide single crystal substrates, which are basically used in the integrated circuit. But it is very important that these material silicon, gallium arsenide that is being used, it should not have any kind of defects and all. And how do we know this? We can actually use XRD to characterize it. Okay, it will easily detect and image the presence of defects within a crystal. So that kind of characterization can be done in the microelectronics industry. Finally, in the glass industry. Now, in the glass industry, you might say that okay, glass is amorphous, and then XRD is not going to be of much help because we are not going to get really a peak. Okay, but the thing is that in glass, if there is any kind of impurity, that can be determined. Okay, so it does not give an XRD diffraction pattern for glass itself, but if they will include any kind of let's say tiny bulk defect falls in the glass, or we need to measure the crystalline measurement of crystalline coating for the texture, or there is some kind of impurity that is there. Okay, that can be actually determined using the glass industry. Okay. So that's all for today, and these are the applications of XRD, which is also important. And before that, whatever we have learned is actually the important parameters that we need to control in an XRD instrument, which you should know. Okay, in case you are going for any kind of experiment using XRD. Thank you.